Hello everyone, I'm Zhang from the Hong Kong University of Science and Technology. Welcome to my video. I hope this video can let you know more about my research topic as a supplement to the post presentation. The topic of my research is through space interactions and clusteroluminescence of poorly conjugated molecules. First, I want to briefly introduce myself. I got my bachelor's degree from Zhang University in China and got my PhD degree from the Hong Kong University of Science and Technology in Hong Kong under the supervision of Professor Ben Zhongtang. Now, I'm a postdoc in the same group. My research interests are mechanisms and photophysical phenomena of aggregation-induced emission, excited state processes, and dynamic luminescent materials. Okay, go back to my talk. For today, for traditional conjugated molecules with luminescent behavior, the photophysical properties could be explained by the classical theory of through-band conjugation. For example, the larger of the pi conjugation or stronger of the DA interaction, the longer of the emission wavelength. The TBC-based theories have guided molecular design and synthesis for several decades. Different from traditional conjugated luminogens, many non-conjugated amino acids, small molecules, and polymers can also emit visible light. They are non-emissive in solution but highly emissive in the aggregate and solid states. This photophysical behavior is called clusteral-triggered emission, CTE. The non-conventional luminescence is termed clusteroluminescence. And luminogens with this property are named clusteroluminogens. However, the traditional through-band conjugation theories cannot explain this kind of luminescent behavior. So, it is necessary to illustrate the behind mechanisms and find more interesting processes. Compared to polymers, small molecules with clear structure are excellent choices for mechanism study. Several previous studies using small molecules found that through-space electron delocalization, known as through-space interaction, is the general mechanism for clusteroluminescence. The overlap of electrons in the three-dimensional space makes the entire molecule have a strong conjugation effect, which therefore decrease the energy gap and make them with visible light emission. However, it is still a challenging to control the strength, the emission wavelength, and efficiency of this kind of interaction. Therefore, several simple and non-conjugated molecules based on triphenyl methyl and its derivatives with electron-donating and withdrawing groups were first studied. Using one molecule, for example, only one emission peak at the short wavelength is observed in pure solution. The emission is from the isolated phenyl ring part. However, in the aggregate and solid state, a new peak at the visible light region is observed, which should come from through-space interaction between three isolated phenyl rings. From electron distribution, we can also see this non-covalent electron overlap at the central position of the molecule. It is a solid evidence of through-space interaction. To understand the working mechanism, we calculate the reorganization energy and compare molecular motions in different environments. In the solid state phase, intramolecular motions are very strong. Therefore, some excitants can decay through the through-band conjugation-based radiative decay channel to produce the short wavelength emission. However, unstable through-space interaction immediately involved with the dark state due to the dynamic molecular motions. As a result, only one short wavelength emission is observed in pure solution. In crystalline state, those intramolecular motions are effectively restricted, which provide a stable excited state geometry and promote through-space interaction. Therefore, some excitants can also relax to the stable state and emit with long wavelengths and bright clusteroluminescence. In addition, we also compare the substitute effect for clusteroluminescence. We found by increasing electron donating ability, the long wavelength emission from space interaction are redshifted, and the quantum yield gradually increase. However, increasing electron withdrawing ability would decrease the emission efficiency and even quench the emission. Then, we investigated the electron static potential and summarized the mechanism. The electron donating groups can provide more electrons to the central part of the molecule, which stabilize the geometry and form the through-space interaction. Besides, it also increases the electron density of through-space interaction to produce clusteroluminescence with higher efficiency. However, electron withdrawing groups push electrons to the outside and decrease the central electron density, which destabilize through-space interaction and finally quench the emission. Therefore, in this work, we successfully manipulated the through-space interaction and clusteroluminescence of those non-conjugated molecules with isolated phenol rings. Besides, we found the introduction of electron donating groups can not only increase the electron density, but also stabilize excited state geometry to further promote the efficiency of clusteroluminescence. Many strategies have been developed to design traditional conjugated compounds. However, it is still difficult to control properties of clusteroluminogens by manipulating through-space interaction. Therefore, based on the previous work, we further synthesized the three compounds with flexible alkyl chain and different halogen atoms, trying to find more interesting photophysical properties. Three compounds show aggregation-induced emission AIE feature. They are non-emissive in solution but can emit visible light in the crystalline state. In the spectrum, they also show two fluorescent peaks within the visible light range, and the intensity ratio excitation dependent. Besides, room temperature phosphorescence is also observed at about 600 nanometers. With the help of theoretical calculation, we find three kinds of transition behaviors of electrons. One is the locally through-space interaction based on the non-conjugated triphenyl imide group. Another one is the through-space charge transfer between two separated units. And the last one is the room temperature phosphorescence with the help of small energy gap and heavy atom effects. These three transitions finally result in the single molecular white light emission. Besides, we also investigate the potential applications of those clusteroluminogens as an organic white light emitter by coating microcrystals on commercial UV chips. And the performance is not bad. This application also investigates the potential applications of many clusteroluminescent materials. Therefore, in this work, we synthesized 3 clusteroluminogens with isolated phenol rings and achieved multiple emissions from multiple through-space interactions. More important, we introduced the concept of secondary through-space interaction. Different from the reported through-space charge transfer based on the largely conjugated donor and acceptor with a face-to-face arrangement. This through-space charge transfer in our work is based on the non-conjugated donor with through-space conjugation. This interaction should be another important mechanism and manipulating strategy for clusteroluminogens. From small molecules, we understand the mechanisms and the manipulating strategies of through-space interaction. Meanwhile, we hope to apply them into polymers to realize the design and synthesis of good clusteroluminescence materials. Therefore, in another work, we successfully synthesized isolated phenol ring-based polymers with near-infrared clusteroluminescence by integrating 2 structural optimizations, including increasing the electron density for through-space interaction and introducing DA interactions. This work also endorses this traditional and commercial phenolic resins with excellent luminescent property, which shows potential to be applied in many areas. Apart from phenol rings, we also utilized the most abundant water as the starting materials to synthesize a series of non-aromatic clusteroluminogens. Using small molecules as models, we studied the structure-property relationship and isotype effects. Furthermore, we have extended this synthetic method and working mechanism to polymers and successfully prepared polymers with yellow clusteroluminescence and 45% quantum yield. Here is a work summary focusing on through-space interactions and clusteroluminescence. We utilize several small molecules as with isolated phenol rings and clear conformation to illustrate the structure property relationship and propose several manipulating strategies. By applying mechanism and those strategies to polymers, we have successfully achieved near-infrared clusteroluminogens and water-based clusteroluminogens and explored the photophysical properties and potential applications. Finally, I really appreciate the kind guidance from my supervisor, Professor Benzhong Tang, and Professor Haoke Zhang from Zhejiang University. That's all my presentation. Thank you for your listening.